Uh, Thanks, Marco. All right, so I'll get started. So I want to tell you about structure formation with warm white noise, or it could have, the title could have been structure formation with warm wave dark matter. Um, so since I use this word warm wave, let me first explain what I mean by this. Uh, so yesterday, Kim already introduced the idea of light dark matter. So as long as dark matter is bosonic and its mass is significantly below an electron volt, then the de Broglie wavelengths of these particles overlap so much and the occupation number is so high that it becomes reasonable to think of this as a classical field. This bosonic field can be a scalar, can be a vector, but for simplicity, I'll focus on scalars, but as you will see, the conclusions are quite general and apply more broadly. All right, so when you think about bosonic fields or scalar fields, then the first thing you have to ask is, okay, initial conditions. What are the initial conditions for the system? How was it produced in the early universe? And again, thanks to the talks yesterday, both by Lorenzo and Kim, I already have a head start. So one option is that your scalar field was globally misaligned during inflation. What this means is that you have a scalar field whose amplitude is roughly constant across many Hubble patches at late time, right? So this is the most common thing that people often are used to thinking about in the literature. But there is, in my opinion, an equally well-motivated case, which is the second one, which is where the scalar field has no constant amplitude throughout space. So when does this kind of scenario happen? This kind of scenario happens, for example, for the QCD axion, when the Petri-Quinn phase transition happens after inflation. If it had happened before inflation, it would give you the first case. If it happens after inflation, it gives you this case, where the field has lots of variations on Hubble scales in the early universe. So it's this second case that I claim can be referred to as warm in this context. Why? Because if you think of this field configuration like this, it varies on this inverse length scale K star inverse co-moving. Then you can take this K star inverse divided by the mass, and you will roughly get what we will refer to as a velocity in the system. Right? So K star over M is like a velocity in the system. So this system already has some velocity dispersion or velocity in the system. And depending on the value of K star and M, this can be warm to be considered, to be ruled out already by observations, or it could be at the edge of detection, or it's warm but not too warm. Right? So it could be in any region depending on that. Okay. So the first case, as I said, Kim mentioned yesterday. The second case, in second half of Lorenzo's talk, we heard about this kind of scenario, but not in the case of axions. We heard it in the case of vector fields. But the same principle applies. So let me try to focus on this case a bit, but towards the end, I will come back and connect both of these pictures together as well. So what implications does this second kind of field configuration have? So if you produce fields with that kind of picture in the early universe like this, then it will have implications for the matter power spectrum, which we can observe at late times. The matter power spectrum at late times has features that are based on 3 distinct scales. Okay? And these scales are just connected to the picture I showed you before. So the 3 scales that are relevant are the free streaming scale, this gene scale, and this K star. K star inverse was the scale over which this varies. This gene scale, in fact, I was trying to prepare beforehand. So you have, in general, this model will be thought of as having 2 parameters, the mass of the particle and the scale K star. Okay? Just 2 things that you need to keep track of. Based on these 2 parameters, we will find that there are 2 scales in the problem. One is K white noise. That sort of determines the amplitude of this thing right here, this diagonal thing right here. And then there is a velocity, k star over m, a combination of the two, that will determine features like this free streaming like suppression that you see here, as well as a genes-related suppression at even higher k. So I hope that as I go through the talk, you'll just keep these scales in mind. Okay? Model is only two parameters, m and k star. And based on that, you can find scales based on which the dynamics are determined. So you get these scale-dependent features rather naturally in the system. Of course, whether these features are detectable or not will depend on the parameters, right? So we can use observations to either hopefully detect them, or if not, we can constrain them. Yes, yes. Okay. I have to mesh this K star to some. Do you have a model in mind that produce this K star? Yes, so for example, if you yeah, so it could be, so in general, so I guess there are two questions. One is whether, what is a model for K star and for any arbitrary K star, or the other case is, do we have a model for K star which gives observably interesting signatures? So which question are you asking? Just general, where do you get K? Okay. Yes. You want to have in particular hierarchy between K star and K genes. Okay. So for example, in the case of QCD, axions produce after inflation. K star is determined rough. It's a combination of the fact that you have the phase transition after inflation, which sets a coherence length, and then there are strings that are produced as well. And the strings create a spectrum that looks like this, or the fluctuation in the field that it produces looks like that, so it creates a peaked spectrum. So K star is determined by those dynamics. In the case of the QCD axion, that K star is quite large, right? It can be, it will be beyond this plot here, that K star. Now, if you create a phase transition later, so for example, if such a phase transition were to happen, say around BBN, okay, or a little bit after BBN, then the K star is roughly the size of the horizon. You should think of K star as inverse the size of the horizon when some process that produces dark matter is produced, right? Or it's a correlation length. Horizon is the largest correlation length. It could be smaller than phase trans to get this value. Right? You can get larger. The idea of K star is much more general, right? It's always there as long as you produce something causally, right? There's a coherence length. You can think of this as in your inverse coherence length of your process. So K star is quite general, but to produce this value of K star, you will have to do a phase transition BBN-ish type thing, right? So that's because that's the size of the horizon then. So if I remember right, it's like 10 to the, after doing the strings and stuff, it might be around 10 to the 9 megaparsec inverse-ish. So it's not just a horizon. I forget what the scale is, what time the horizon is at that time, but it's connected both to when the phase transition happened, but also there the strings are actively whipping up more axions later, right? So because there's a strings there. So it's a slightly more complicated scenario with QCD. Like, no. Peak moves, yeah. 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 So yeah, exactly. So that part, so QCD is particularly complicated because you have this active sourcing that's going on, right? But still there's a scale K star, right? So somebody can give me a model with a K star value. You can do the entire calculation, right? But even if you don't give me a K star value, as I'll show you, the results are, at the end of the day, it's just an input, right? You will see that the features roughly will still be there. Okay. The number is an input, but the features will still be there. Okay. Right, so I mentioned that there are these two scales in the problem, K free streaming and K genes. I think for this audience, I don't have to say much, but just in case you haven't heard about these scales. So K free streaming inverse is basically roughly the co-moving distance that particles travel from the time of production till whatever time you're calculating, right? So it's a length. How far do they travel? K genes is roughly a length scale below which stuff cannot gravitationally cluster. As you can imagine, both of these are linked to the velocity dispersion in the system. Okay. So these are sort of the scale-dependent features that you get in the matter power spectrum in all of these models. Is this of any use? Well, the first things we did was by noticing very roughly that these features are not yet seen in the data, we were able to immediately put a bound on the mass of the dark matter particles. So because free streaming and this suppression things are related to K star and M, we were able to say that we don't see these features, so it tells us that the dark matter mass cannot be lighter than 10 to the minus 19 eV. So straight away, in a very simple way, you can put constraints on things like that, as long as this dark matter is produced after inflation. Why do I say it's so model independent? Because causality restricts the fact that you can't have correlations beyond a horizon scale. Right? So if it's produced after inflation, you naturally build in a K star, and working through it, you get this, this bound. This is K star independent. And towards the later part of the talk, I will show you how it really becomes K star independent. Because we just want a bound, it becomes K star independent. Right? Yes. 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 I mean, the bound won't, because we use both features, right? But in that case, you will get a bound on K star, but not on M. Okay. So here I mean, basically the bound will, I mean, I think you will, it can be light, it cannot be lighter in that case still than this. A bound, sorry, I should be more careful. The bound still holds, but it's not coming from free streaming, it's coming from K star, right? Okay. Bounds are all wonderful and great, but that's one aspect of it. We want to actually find out what dark matter is. So we want to actually look for these features going forward and hopefully detect them, not just put bounds. As you go to smaller length scales, especially this scale right here, as you might imagine, things are going to get nonlinear. And as things are going to get nonlinear, there's going to be fun things happening. One of the fun things when you work through the numerical simulations, you will find that you get very dense structures that form on small scales. Okay? So there's a lot of early structure formation because of this enhancement on small scales. And these, if you're doing wave dark matter, this will go under the name of mini clusters, solitons, etc. Okay, but I will show you that this is not just about wave dynamics. It's still, some of these effects are there in particles as well. Okay, all right. And this puts me into the next slide. Even though my talk, I titled it Structure Formation in Wave Dark Matter, the reality is that what I'm talking about can be applied to any collection of massive objects that are somewhat rare, meaning their co-moving number density is not essentially infinite, okay, that they're rare. And I'll show you what I mean by that. If you have this and these things have some velocity dispersion, then the same effects that I'm describing will still be there. So for example, these dots here could have represented in wave dark matter, they're what are called interference granules. They could be primordial black holes, for example, or they could be composite objects like solitons or mini clusters. But the effect and the description will still apply. All right, so that's sort of the main takeaways. Now, the important part. So first, let me just thank the amazing collaborators. I think Mehrdad, I feel like many people here in the audience know, this stuff started, I think it's of Italian origin, I can say, because it's started when I was visiting Mehrdad in Trieste a few years ago. So it started with that. Then we've extended this in later works with Mehrdad and other collaborators, including Xiang Ling, who was a graduate student at Rice, where I'm from. Sten Delos is a fantastic postdoctoral fellow at Carnegie Observatories, and Simon Mai, who is a postdoctoral fellow at the Perimeter Institute. So, of course, a lot of the things here would not have been possible without these wonderful collaborators. Okay, and Mehrdad will be here, I think, in the last week, right? So week 5, okay, week 5. Mehrdad will be here in week 5. I guess we have, even though we thought about bosons, we have decided to be fermions, so I will leave precisely when he arrives. Okay, so let me go into a little bit more detail, and please stop me if you have questions along the way. So the plan is I'll say a little bit more about models. Diego has already asked questions about models, but hopefully this next slide will say a bit more. Then a little bit about the physics and analytics, simulations, and eventually applications. So I guess the first question, which to some extent I've already answered, is are there models where you produce these variations? And my answer is that anytime you produce, essentially anytime you produce dark matter after inflation, you have these, at least this wave-like dark matter after inflation, you will have this sort of behavior just from causality considerations. This happens in, as I said, axion-like fields, including the QCD axion. It can happen when you transfer energy from, say, a reservoir, like an axion field, to dark photon fields. Again, you will have this kind of a behavior. You will have a peak. You have this kind of field configuration at the end of it. Indeed, as Lorenzo yesterday mentioned, even if you have inflationary particle production, not after inflation, for the case of vector dark matter, you again have this kind of behavior in the late universe. Okay, so it's general. It's not something I'm very specific, a very specific model. This kind of field configuration in position space corresponds to a power spectrum of the field. By that I mean this Q cube P of phi that is peaked. It's peaked at roughly the coherence length here, which is K star. This is co-moving. We're going to start thinking about these things once this scale K star is subhorizon. Okay? So it's subhorizon, and once it is non-relativistic. It's not that we can't do the calculation when it's relativistic, it just makes life much easier to do. So I'm going to assume that at least for the purpose of this talk. Okay? That we start doing the calculation once the spectrum is established. It's non-relativistic and subhorizon. Non-relativistic part, I think you really can't get around that because this is supposed to be dark matter, so it has to become non-relativistic. Right? And it also has to be subhorizon at some point, right? As the universe evolves, this will happen. So it's not an assumption, it's just we're choosing a starting point. Okay. And by the way, here again, Zach, you'll ask questions along the way. So Zach, of course, also has models which will generate similar peak spectra at the end as well. Okay. So what is the relevant physics here? Okay, so let's start with the first bit. Okay. So if dark matter energy density is dominated by these sub-Hubble modes, right? So remember, the fluctuations are in the field, and that is what is making up the energy density of the system. Then there are two effects. One, this is what we will call this isocurvature enhancement on subhorizon scales at early times. And then there is the usual large-scale adiabatic component. Again, Lorenzo mentioned this, that you should expect this to be there in general. You can calculate it or so. So let's try to understand these things independently first. So why is there this shot noise like component? Well, the silly thing to do is to just take this power spectrum and calculate the density fluctuations. If you calculate the density fluctuations based on this power spectrum and you calculate it at wave numbers smaller than this, much smaller than the scale K star, you will find that it becomes independent of K. If it becomes independent of K, that means it's shot noise. Right? So K cubed P of K will just go as K cubed. So that's your calculation. If you don't want to calculate, you can just realize that this is a causal process, which means there'll be causally disconnected Poisson distributed density fluctuations. Poisson distributed density fluctuations means that the power spectrum of that will be white noise. So physically, again, it's just causality that will enforce this. Right? So here is a visualization of that. Here are these patches. In here, if you look at the power spectrum of this density field, it will look basically like this. It's cut off roughly at the scale of these blobs. Right? So that's why you get this shot noise contribution. You produce fields and you will get this shot noise. Now, these fields are, of course, produced, on very large length scales, they produce inside the background of curvature perturbations produced by inflation. So they have to respect that as well. So as a result of which, if you look on very large length scales, I've just shortened this by changing my length scale here. This really is extended far away. This is the adiabatic part. So how does, and the way I think yesterday Kim and I were discussing, so hopefully, and that seemed to get the idea across better, so maybe I'll try to do that here as well. So the way to think about this is imagine producing the fields locally inside a Hubble patch with whatever process you have. And now just modifying the energy density, or if you want the field amplitudes in such a way that it respects long wavelength adiabatic perturbations. So you just take your adiabatic perturbation and modify the field amplitudes ever so slightly, or the density ever so slightly, so it respects that, right? So that's how you would generate these initial conditions. And of course, in nature, this should happen naturally. Okay, so how does the system evolve? So first, let me show you this is a spectrum, and this is a physical space picture of what the spectrum is doing. So on very long wavelengths, indicated by this blue, you see this long wavelength adiabatic perturbation. On very short length scales, you see these blobs, these causality-related blobs. This orange part is the isocurvature part. The long wavelength part is the adiabatic part. And now we let the system evolve. So what will happen? So here is what you will first let me show you what happens visually. So notice that this long wavelength perturbation has gone away. Right? It has been erased. Right? But you notice that the short wavelength perturbations still remain. Okay? So what has happened is the long wavelength perturbations are correlated. They were genuine density fluctuations. This field had velocity dispersion in it, so it tries to move around. It homogenizes the system. Right? So that's why this correlated density fluctuation disappeared, because free streaming erased it. However, you notice that the isocurvature part, which is related to these short wavelength fluctuations, those things just move around. So statistically, the system is no different than it was before. So that part doesn't change. So that's why this isocurvature amplitude during this period, which is during radiation domination, no gravitational clustering, remains fixed as it is here. So the adiabatic part will undergo an erasure because free streaming erases correlated perturbations. Isocurvature is uncorrelated in this case, right? So it doesn't get erased. So this is essentially the reason that you are expected to see a dip from free streaming. This is a usual warm dark matter dip that you expect from free streaming. Yes? For a person who, of course, does simulations, it's an absolutely correct question. So this is actually, it's even more trickier than that, because the simulation is done with the full spectrum correctly. But when I show this, I've actually filtered, right? To just show the effect. Otherwise, you would be swamped by the small scale things because the peak is there, right? So I filtered it to just show the effect. Right? But the simulation, of course, does it with the full spectrum. Yeah. Okay. Yes. Right. So yeah, so it certainly, it will, so here this is, that's why I've not put numbers there, right? So how far this comes about, it depends on time, which means it will depend on how early it was produced. So there are two things, right? When was it produced and what was the velocity at that time? Both things matter. It's not just the velocity alone, and it's not just the time alone. Both things matter. How far have you traveled? So certainly it depends on that. So to give you since you asked, so K-free streaming, you can write it down in terms of parameters of the model as follows, and this I'll write in terms of things that are perhaps more. Okay. So sigma is the velocity dispersion in the system. Okay. you evaluate it. If I evaluate this at equality, I'm just doing this right here, then the free streaming scale is roughly the K equality, and then it depends on sigma equality in this way. Right? So this has included the time and everything, included, all of these effects included. So once you include all of that, because you will find that the answer just depends on sigma equality in this way. So when you look at this expression, it seems it's time and sigma, but once you have done the integration, because it's just evolving through radiation and matter domination, which we know, then you will find that the answer just depends like this. Okay? While we are at it, notice there's a log factor here. Okay? If you try to write down K genes at equality, this will just be, I should write, K equality over sigma equality. Okay? So the free streaming length will always be longer than the gene's length. Okay, so back to free streaming, so you see this effect, right? So whether it's observable on an observable scale or not depends on parameters, but there will be a dip, and it will be given completely in terms of the sigma equality. Yes? Then you can erase those fluctuations from free streaming. So the fact that this is truly random noise that's just moving around during radiation domination is relevant, right? If it is correlated, it will get erased. If it's uncorrelated, you can't wipe out. I think they trying to make it a catchier phrase, right? White noise is zero correlations. You can't erase zero correlations. Right? There's no way to do that. If you give me correlations, free streaming can erase them. But if there are no correlations, what am I going to do? Right? It remains as it is. Right? Yeah, you can get rid of the peak. I think you can get rid of the peak, and it will. I mean, the scale at which you are suppressed is just determined by this. Like, this is the end result, right? So for example, if you want to get away from waves and stuff, even if you had warm dark matter, if you put a peak in the spectrum, if your free streaming length was below that peak, you would erase that. Right? K was below that, you would erase that. Okay. So this is somewhat of hopefully this is clear what was going on here. Now let's get to, so this was during radiation domination. Now let's get to matter domination. Now both of these parts, the adiabatic part and the isocurvature part, both behave the same essentially, right? Both can grow, right? They just grow during matter domination. So you notice on top, I've just seen the curves go up. And this roughly goes as scale factor squared, the usual matter dominated growth. There is a little bit of notice that I've put a scale dependence in the isocurvature growth, and that's because of what I just mentioned, that there is also a gene scale in the problem because of the velocity dispersion. So that introduces a scale dependence there. Right? So there's a free streaming scale that's relevant for everything that happens during radiation domination, and then there's a gene scale for everything that happens during matter domination, and they're distinct. In fact, for the models that we have looked at, they're roughly separated by a factor of 6 to 10. Okay? So they're separated from each other. And below, we're just showing so the previous simulations, or the pictures I was showing you were from relativistic simulations, although they didn't have to be. These ones I'm showing you are now from non-relativistic Schrodinger-Poisson simulations, including gravity. And you can see the formation of structure from, you can barely see the fluctuations there to growth of structure, nonlinear structure on the right. Okay, so just to summarize what I have said, if you produce dark matter fields causally after inflation, then you expect at early times to have a power spectrum that looks like the one on the top. There is this short noise part, and there's the adiabatic part. You evolve it through radiation domination, then you will end up with the power spectrum that I show in the second tier below, meaning there can be some free streaming suppression because of stuff moving around. You get to matter domination, and you start growing structure. Everything will grow, but there will be some suppression below the gene scale because the system still had a velocity dispersion. So again, these three scales that we talked about before are coming into play. Okay. Let me show you a little bit of evidence that so far I've only talked in terms of pictures and so on. Let me show you that we've done a calculation, which I'm mostly not going to talk about in detail. But we've done a calculation, and based on that calculation, we can predict the evolution of these spectra. For example, here, this is for, I'm only showing the isocurvature part. I'll show the total in the next slide. The solid lines are from the analytic calculation. The dots are from a Schrodinger-Poisson simulation. The simulation starts at a redshift of about 10 to the 5, and in this case, it goes to about a redshift of, I think, what was it, 30-ish or something like that. Okay. So you see the formation of structure, meaning the power spectrum grows in amplitude in that scale-dependent way. There is something on the top that you see, that there's a gray band. That's basically nonlinearity. So our calculation, analytic one that we can do is, of course, is going to break down when you get to nonlinear scales. And you directly see that the data, that the simulation points also deviate once you reach nonlinearity, as expected. Okay. But we can predict that. And we see in the simulations, these were run by Simon Mai, we can see the growth of structure there. And it matches very well. Again, the dots that you see here are the gene scale, and the dot and the location where the bend appears up there, right? Like where does it bend over? That's a gene scale at equality. After that, it's suppressed. So it's just this number. It's K equality. Again, now maybe putting in numbers. Remember, K equality is about 10 to the minus 2 megaparsec inverse. You take sigma equality to be whatever your model you want in your model, and it will tell you what K genes is. So it will be larger. This sigma is, of course, in apologies, I sometimes switch between, I guess, particle physics and astro units. Here, C is 1, so sigma equality is much smaller than 1. So this is, this K genes will be much bigger than K equality. Yeah. This will match roughly, yes. So ratio of, yeah, that's about right. I mean, there is already, no, even before that, right? Like, so the deviations are actually, in this model, or this parameter choice, the deviations will start happening around 10 megaparsec inverse. I'm not showing that yet, right? Because this will, for this to connect, let me show you the next plot. And this, I'll explain in a second, right? So your lambda CDM is coming in, right? I'm not showing the usual part. Your lambda CDM, let me just draw it. So K cube P of delta and K. Your lambda CDM plot would look, this is a log part, this is K equality, roughly right here. Imagine that somewhere around here, okay, for this parameter choices, you will start, if free streaming was not there, you could imagine seeing a deviation like this in the plot. Okay. So this can be around, we chose 10 megaparsec inverse just to say that, okay, this is safe from data right now. It's not, there's no other reason to choose that, right? And this is where the bound comes from to some extent. So we just chose this to be 10 megaparsec inverse, but you could move it to either side. Here, what I'm showing you is not just that enhancement, but I'm also showing the free streaming suppression. Again, the simulations show that as well. Okay. I told you I won't show you much of the calculation, but I still want to tell you how this all works, how the analytic system works. And this really, I know it probably will look horrible in the next couple of slides, but it really is beautiful and it's fun to do. So especially if the people who are younger than I am, if you want me to go through it on the board later, I'm happy to go through it. It's beautiful calculation in the sense that it's very general. Okay, so what do we do? So we start with the field equations, right? So there's a step before that, which is, you start with the relativistic equations, you boil it down to non-relativistic systems, which is the Schrodinger-Poisson system. You take the system and you can translate it into a language that is centuries old, which is a century old. This is BBGKY hierarchy, right? So this hierarchy is what people in astro as well as in plasma physics have been familiar with for a while. This is the idea of how to evolve basically phase-space distribution functions. One particle phase-space distribution function, two particle phase-space distribution function, n particle phase-space distribution functions. Okay? And this is a coupled system, which if you solve it completely, then you have solved the problem exactly, but nobody's ever going to do that. So it's like the Boltzmann hierarchy, just a different way, right? It's a different way of thinking about it. And what you can show is that you can translate this problem into thinking about one particle and two particle phase space distribution functions. And this two particle phase space distribution function is really what gives you the power spectrum. In fact, for people who are familiar with Boltzmann things, you usually work with the one particle distribution function. And that's because you allow for the system to be spatially inhomogeneous. You say you're working in a fixed background. But if you insist that you have true statistical homogeneity and isotropy, then you would have to work with the two particle one. And that's what we do, but again, it's details. And based on that, you can get the power spectrum. And this idea, you can either start with the wave picture, or instead of this, you would just start with Newton's laws. That's all, right? This is also Newton's law in an appropriate sense. And then you can work forward for particles, for black holes, for whatever you want to do. So it's very general, this way of calculating things. So I think the first paper Meredith and I wrote is probably too short. The second paper Meredith, I, and Sten wrote is probably too long. Somewhere in the combination of the two is the right level. But the second paper has all the details. Okay. So let me tell you how the calculation works out. Just one slide in practice. You give me an initial power spectrum or a phase space distribution function. Either one it's equivalent, right? You can just translate the power spectrum of the field to a phase space distribution of particles, just match the co-moving, what we think of as wave number, match it to the momenta of the particles appropriately. Okay. You do this, and you will calculate what are called free streaming kernels. These are just integrals over the phase space distribution function. Don't need to worry about the details. They're for things like Maxwell-Boltzmann or simple things, they're analytic, right? Like you can just get analytic expressions for these things. Then is the main meat of the calculation, at least as far as what is supposed to be computed. Then you have to calculate the time evolution. This T, A, B, and C are transfer functions. What they tell you is take an initial density perturbation, how do you transfer it forward? You take an initial velocity perturbation, how do you transfer it forward? The C one is a little bit tricky. It's related to the short noise part. If you are interested, I can tell you more about it. But they all solve essentially the same equation. It's a Volterra equation. For people who are familiar with warm dark matter, you know that you can't write down warm dark matter systems as just a differential equation. It's always an integral differential equation. Okay? In the same way, these are also integral differential equations. Okay? They care about the history. So you have this equation, and you can solve this system for each K mode. So again, you can solve K mode by K mode once you have done this. And once you do that, you can find the transfer functions for the adiabatic and isocurvature part. And again, I'm separating them, but the whole calculation, the calculation gives you both together. Something that's quite interesting, the adiabatic part, as usual, matches what you all probably already know, what happens with free streaming, what happens with usual growth. All of these things are already inbuilt, already come out from this calculation, just as before. But the new bit here is that because of this part, we didn't know how to evolve using standard techniques. So this is the only way we knew how to do this with this two-point correlation function. And that transfer function looks different. How does it look different? Notice, first of all, that this T iso transfer function has a product of this B and C transfer functions, which are the velocity transfer function and the density transfer function. That's still okay. It's a product, just like before. You would square transfer functions usually. But the interesting thing is that now it's an integral in time over that. So this feature is somewhat distinct, but it works. And I can tell you a little bit of the intuition that we have developed about how this is coming about. But this is what comes out, and it agrees with the simulations you can do. So if you're interested, I can take you through the derivation as well. Okay, but let me sort of getting close to the end, so let me just get to applications now. So for the applications part, I've already mentioned that you could just use this system, and you could get a bound on the dark matter mass. How do we do this? We say, well, just very roughly, from Lyman alpha data, we don't see an enhancement of the spectrum below 10 megaparsec inverse. So that gives a bound on K star. You can also say that, okay, from observations, we don't see a suppression of the structure. So no free streaming is visible there. The combination of those two, you use the fact that both K star constrains the enhancement and K star over M constrains the free streaming, The combination of those two observations allows you to get rid of this K-star dependence and get a bound on the mass independently. So it's sort of this is very roughly, if you were to plot, say, which way? I hope I'm plotting it the right way. K-star, no, M versus K-star. M versus K-star. If you were to plot this bound that K-star cannot be smaller than this value means that you are not seeing the isocurvature enhancement. And the fact that it cannot be this region right here comes from the fact that you don't see free streaming suppression. This doesn't mean you know what the value is, but you can get a bound because this is the lowest value the mass can have. Okay? So that's how we get a bound without knowing K-star. Just not all these observations come in with different sort of systematics and different assumptions, so you shouldn't compare them. They're not apples to apples comparisons. But roughly, this is the bound for this type of dark matter is at least comparable to the bounds that exist in the literature for the mass of dark matter particles. Yes. This, good point, Fabian. Yes, I will get to the text. This is all, right now I've assumed this is 100% of the dark matter. Okay. If your constraints will change in interesting ways. Okay, it's not just saying it's going to go away with fraction. It changes in interesting ways if you make it a subfraction. Okay. By the way, I was telling you that there's nothing about. I motivated this with waves, but you could have done this with just 100% fraction of primordial black holes. I know this would be ruled out by other data, but just to give you a sense, if you were to play the same game, you would get a constraint on the mass of the dark matter, of the black holes, of a few hundred solar masses, right? They have to be heavier than that if it was 100%, but of course other observations ruled it out. But you can use this here as well. Okay, yes. 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 So this just assumes that 100% of the dark matter was made up of these black holes, and you produce them in the early universe with in a random way, right? I think I'm not so sure because I haven't thought about what kind of correlations it sets up on small scales. But if you produce these things after inflation, right? Suppose you had a true to after, but I'm saying that, yeah, I understand that it is after inflation, but it's if there are no correlations on subhorizon scales, which is the assumption I've sort of made at the time when I start, or roughly no correlations, then this will work. But if they're perfectly correlated, you can't kind of use the same arguments that I've used. Yes. Yes. So again, you shouldn't take the black hole one I'm just showing here because it's kind of a absolutely. There are many things that would be better than this bound that I'm giving on total black holes. This level of black holes have already been ruled out, right, by other observations. So I'm just saying you can do this. I'm not suggesting this is the best bound. Okay. Let me, okay. By the way, for people who do structure formation, just a small thing. We can, based on this power spectra that we are able to calculate analytically, we are able to also calculate mass functions, halo mass functions, right? And the halo mass functions we have also validated with the help of simulations, and they agree, right? So they both agree. The power spectra can be used. You have to be a little bit careful when you calculate halo mass functions because there's a gene scale, so you have to cut it off there. It's kind of press Schecter-like, but not entirely. Yeah. Yes. 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 Please. I think, but this is not asteroid mass, right? This is hundreds of solar masses. Yes, so it rules out bigger black holes because the bigger, you can't, sorry, did I say it incorrectly? I had the wrong sign up there, sorry. Okay. Yeah, so it rules out masses bigger than that, sorry. I had a wrong sign in there, yeah. Okay, that makes sense why you were asking that question as well. Yeah. Okay, so the mass function agrees with the predictions. You notice, so the top one is for particles, the bottom one we did for waves. You notice the waves one, compared to the solid line, doesn't match as well. And again, there's a physics reason for why it shouldn't have matched so well. At least that's our guess right now. And the reason is that for the wave dynamical case, at the center of all the first halos that form, you end up having a soliton at the center, right? So solitons are these coherent configurations of waves that are really stable. They're the lowest energy configuration of the system. And I'm not quite sure how to, as yet, how to handle them a priori, right, in the usual press-tractor-like formalism. But I think we'll work through this because right now we don't have all the details, but they're definitely solitons. And they essentially, every halo that forms at this early time, as soon as it forms, there is almost instantaneously there is a soliton in them at the center. And their profiles and everything matches. Okay, I think I'm almost towards the end, so let me just say, I hope I have convinced you that if you're going to create dark matter and it's dominated by sub-Hubble field modes, then you will have this isocurvature enhancement and genes and free streaming related suppressions. You'll have this extra features like mini clusters, solitons, etc. They can be useful in terms of bounds or as probes of formation mechanisms. And there's a whole framework now of how to do this calculation. Just extending it a little bit beyond, and this goes to Fabian's question, and of course you should look at work from some of the organizers of this meeting as well as from Fabian recently about considering mixed cases very recently. But the formalism that I've shown you extends to the possibility of you having only a fraction of the stuff which has the isocurvature enhancement. Only a fraction of the stuff has the free streaming. It's general enough and you can calculate all of these things. Hopefully there'll be a paper from us on this as well soon. And you can get constraints based on that as well. One thing I did assume here is that all the interactions once this stuff is produced is gravitational, right? So I have assumed that there are no non-gravitational interactions after this dark matter is produced. It just evolves under gravity. In principle, this formalism is capable. All it needs is, in some sense, either a cross-section or you feed it in and it can still, right now we've used a gravitational cross-section to calculate. You can just feed it in and you can calculate it for other interactions as well. And it would still give you this result. But of course, I can't say anything about this because we haven't done any calculations yet to tell you what's going on. Okay, with that, thank you very much. If you want to see movies, let me know as well. I have some movies after this, but I'll open it up for questions. Yes, please. Okay. I'm going to go out of my domain of expertise because I haven't thought about it enough. But okay, so the subtleties of which part were you referring to? Which part of the subtle? You said subtleties? Sorry? Oh, solitons. Sorry, I heard subtleties. And I'm like, there are many subtleties everywhere here. Okay, so solitons. So first for people, I mean, if you know, I apologize for the introduction again, but so solitons are localized configurations in the field that are usually waves want to disperse as a ripple in a pond, but if there's some nonlinear interaction, it wants to hold it in place. So the balance between the two is what creates a soliton. In this case, the solitons we are talking about, the nonlinear interaction is just gravity, okay? But it's not just a bound object, it's a coherent system, meaning the phase of the field throughout this object is exactly the same. So it's oscillating with the same phase. So it's a phase coherent object, and that's the soliton here. How would you see them? One way of potentially seeing them based on the effects I'm saying is that solitons will be also rare objects, right? So they create a shot noise. Okay. So the shot noise will give rise to this isocurvature enhancement, and that's something you can hope to see, right, on the large length scales. This is the effect of shot noise on large length scales. Even if they're a subdominant component, the shot noise effect, so suppose solitons form fraction F of the total dark matter density, then the shot noise enhancement goes as F. So this is solitons, this is solitons, right? So number density, so F squared is a fraction of the total dark matter density squared. divided by the number density of the solitons that you've produced. So this ratio, this would be what determines shot noise. So you can get the same amplitude of the shot noise, even if the fraction is small, by making them rare, up to a certain limit, because otherwise the formalism breaks down, and you have to treat them as individual objects. Okay, so you could detect them because of the shot noise effect. The other thing is that these are small things, and you can look at local, smaller scale, not large scale structure, but small scale structure observables. You could look for things like lensing. You could look for these things based on probes like how stars are moving around in the centers of dwarf galaxies. And so one example, a very nice work, the idea is older, but perhaps the most popular version of this is by, paper is by Neil Dalal and Andrei Kravtsov, where what they first asked, these wavy stuff has interference patterns, so it kicks stars as they move around in orbits, so it increases the velocity dispersion of stars. We don't see the velocity dispersion, so that put a constraint on the mass. What would a soliton do in this case? A soliton at the center acts as a big spoon, and it stirs the system up even more, right? It's jittering around a lot more, so it can increase the velocity dispersion of the system, and you can see the effects. So those are gravitational effects, right? And again, the usual lensing, et cetera, things could apply. The other perhaps effect that I've not talked about at all here, because I'm focusing on gravitational interactions, is that if these were axions, then axions, we've talked about this coupling already yesterday. Axions have, so let's say phi is the axion, you have phi FF dual coupling to photons, our regular photons. These solitons are giant lumps with a high coherent field amplitude in the center that's oscillating. That oscillation leads to a strong oscillation in phi, which through parametric resonance, again, or tachyonic resonance to an extent, can create lots of photons. So these things can go off in a flash, and you could observe those flashes as well. You could say, why don't we see them? Usually, if these flashes were to happen, they have already happened, right? Because the timescale of the instability is very fast. But one way of seeing them today would be if two of these things were to merge. So they're below threshold before. Once they merge, again, an instability is triggered, and they go off in a flash. So people are looking for these things as well to see the non-gravitational impact of these kinds of objects. Yeah. Yeah, very good question. Of course we are. We haven't done the detailed calculation. Right now, Simon Mai, we are running a simulation at least with simplified feedback in the system, and we are trying to understand. I think of course, we didn't go to a simulation first. We did the estimates of the baryonic gene scale, okay? And we found that you should still see this enhancement, okay? It will be modified, where you see the bend, that's roughly where the baryonic gene scale lies. So you'll start seeing it near the bend on the top, not the lower bend. So I think the lower part should still be safe, but we are still going to run simulations and see, because we are first doing it without any feedback, then we're going to run it with feedback to see what the effects are. But I have no answers at the moment. We haven't done it yet. I think I forgot to mention, by the way, I think Diego, you asked a question at some point about the K star, what models can give you something. And I think I was talking to Michael this morning, he's going to talk tomorrow about late phase transitions, right? His late phase transition. I agree. I agree. I agree. That could very well be true. I don't know of a model. It's challenging. I would agree. Yeah. But I think it depends on the philosophy, right? So our philosophy here is, look, it's philosophy, right? So I agree with you completely that I or Medard or any of our collaborators, we don't have a model to say, this is the model we're trying to rule out. We're saying, this is what observations can do right now, right? You go to higher K star or higher M, typically you will need observations at smaller and smaller length scales, right, to do that. But I was going to mention just that phase transitions, and as you said, right, that Michael is going to talk about yesterday, if it happens around, he's going to talk after equality. if it happens around BBN, which is much earlier, even if you were to produce a fraction of the dark matter, I think there will be, the short noise effect will still be there. Also, because you're producing it so, even as a fraction, and if it is produced, because it's produced so late, the velocity dispersion doesn't have enough time to completely redshift away. So you will have a free streaming effect as well, but the free streaming dip will not look like a full dip. It will be a shelf, right? So like neutrinos. So there's a subfraction that is causing free streaming. So you'll still have an effect on these scales now, but it will not be a suppression that just goes all the way down. It will become a shelf like we see in neutrinos. So that's what you would expect if you have a fractional case. Yeah. Yeah. No, no, no. There are many scenarios to make that emerge yet. Like, in fact, I would say most of the scenarios, I mean, okay, people will argue with me, but most of the scenarios, whenever you produce any field after inflation, so let me give you a specific example. The very specific example is QCD axion. Perhaps one of the more familiar examples. Like QCD axion with PQ transition after inflation does exactly this. It creates a spectrum. If you produce suppose you have a reservoir field and you're going to produce dark matter from it, right? Again, if you do this after inflation, causality considerations will produce exactly this kind of spectrum. So almost any time you're going to do things after inflation, you're going to have this spectrum. So all models will do this. Scale, right, exactly. Yeah. Yeah. It's just whether scale is in the observational regime or not is a challenge. And that's a model building challenge, right? Like, are there many models that do that or not? But the generic features that you see should always be there. Okay. Yeah. Yeah. Oh, my favorite question, which it seems like you're a plant. Okay, so solitons, if they're scalar field solitons, they have no intrinsic angular momentum. In fact, if they're perfectly ground state, there's no angular momentum in the system. But you can excite them and then they could have some angular momentum modes. But those will dissipate. However, I only have talked about scalars. Imagine your dark matter field is a dark photon. Okay? Dark photons is a vector field, and a vector field can rotate in a circle. Okay? A soliton made up of vector fields generically has a huge macroscopic amount of angular momentum. Because the entire object, the field everywhere in the object is spinning. Even if it's not a circle, it's an ellipse, right? So it's a combination of linear and circular polarization. You will generically have a lot of spin angular momentum. And so, okay, now you've mentioned it. Okay. Let me see if I have there, okay. So this is a separate talk, not this talk, all right? So here's what the vector field does if you have a vector field dark matter, if you try to ask what is the field doing, the field will be doing this kind of behavior. This is actually from an actual simulation, right, with gravity and all that. So it moves around and typically in ellipses. And if you look at any condensed soliton in the system, you will find that the spin density all points in the same direction. This is spin angular momentum. Spin angular momentum is just the cross product of the vector field and its time derivative. That's what spin angular momentum is for a classical field. Okay? It's not orbital angular momentum. Nothing is moving around in a circle. It's just the field is rotating. Right? So these objects, these solitons, will have huge amounts of angular momentum. But now that I've shown you all my excitement, let me tell you why this is exciting, but observationally not so much. The reason is that Newtonian gravitational physics doesn't know anything about spin. It doesn't know anything directly about angular momentum, right? If you tell me an object, Earth is spinning, and you ask what the gravitational field is here, the gravitational field here knows nothing about the fact that the Earth is spinning, right? So it doesn't know about angular momentum. So it's, in that sense, of course it knows it's still a conserved quantity and so on. So if you have a soliton there that has huge amount of spin angular momentum, if I stand far away and ask what are the gravitational effects, in a Newtonian sense, I see nothing. On the other hand, if you now couple this If you do go in the GR regime, certainly spin becomes relevant, and you can think about this, and we've done full numerical GR simulations, and they change gravitational waveforms and all of those things. There, that's interesting, but not for structure formation or for these kinds of things. The other way you could get very interesting effects is you couple them to photons, because now the photons that are produced will be polarized. Okay? So you could look for these signatures in that way. Thanks for asking. You see, I didn't mean to talk about this, but thanks for asking. Here's sort of a, no, not this one. Here is a movie of these solitons with spin. Actually, no, this one is without spin, but them emerging from generically, right? When structure forms, as time evolves, these are lowest energy states, so they condense rather naturally in many different systems. So you can see them forming. So here, this was supposed to be inside a halo. This is, both of the other two are in the early universe when they're forming from early universe initial conditions.